The escape speed or velocity, if direction is stated, we're not worried about that here. So we're just going to talk about speed, is given by the following formula. V equals, which is again velocity, but here's speed. V equals the square root of 2gm over d. G is this universal gravitational constant given by 6.67 times 10 to the negative 11 with those units there. And the mass of the Earth, we can assume it to be constant, though technically it's not. Gases, well, yeah, gases get leaked out into space, and meteorites hit Earth, so its mass fluctuates. But we can talk about constant right at this moment as 5.9722 times 10 to the 24 kilograms. We're going to rearrange this relation as a single constant with negative exponents. So what's important to note here is that 2gm, this is all just a constant because these numbers are given and we're saying they are stable. What's changing here is d and v. Those are the real variables in this equation. So what I can do is I can split up the radical over top and bottom. I could split up the radical over each 2g and m as well, but those are all just a constant anyway, so why split it up? I can break up the radical over top and bottom, and I could say that 2gm, this is just a constant by itself. I could say it's constant c, for instance. And I want to use negative exponents. Well, d, by rules of radicals, this is the same thing as d to the 1/2 power, right? 1 over the power of the radical. This is a square root. And this is the same thing as saying c d to the negative 1/2. Of course, here we're saying c equals the square root of 2gm. And we can actually calculate this value by plugging into a calculator. We have the square root of 2 times g is 6.67 times 10 to the negative 11, and m is 5.9722 times 10 to the 24. Let me just make sure that's not. Okay, yep. 28 million, we'll just say 28 million or 2.8 times 10 to the 2.82 times 10 to the 7. 1, 2, 3, 4, 5, 6, 7. Yep. So 2.82 times 10 to the 7 with a certain units there if you multiply them together. I guess that would be, well, just the kilograms would cancel, so you just have meters cubed over second squared. Okay. How are escape speed and distance related? Well, we have d to the negative 1/2 and v. Because of that negative power on the d, then as d increases, the negative power means that v will decrease, and vice versa. As d decreases, v will increase. As you get further and further away from the thing with gravity, the velocity you need to escape, the escape speed, I should say, that you need to escape that gravity is less and less because the gravity affects you less and less. And vice versa. As you get closer and closer to the planet, you need more and more speed to get out of there. So they're inversely related. As one goes up, the other goes down, and vice versa. Okay. The Earth is to assume to be a sphere. So if the Earth is a sphere, then this is the radius. And what you can think of the Earth as is a point right in the center of the center of mass. So if you're on the surface of the Earth, that's effectively you're saying you are 6.371 times 10 to the 6 meters away from the thing that enacts the gravity. And that thing gives you this gravitational constant with this mass, and you can use this equation. So effectively, we're just saying d equals 6.371 times 10 to the 6 meters. So what's the escape speed at the surface of the Earth? Well, it's going to be v equals this c times 6.371 times 10 to the 6 to the negative 1/2 power. Of course, we're talking about radicals here. you can distribute this power over this. And of course, the square root is the same thing as this 1/2, so you can just do the rules of exponents there. And using this c here, we can calculate the whole thing together to get a number. So let's go ahead and do that. We already have c there. C is the answer. Times, let's see what the, yeah, I'm going to do 6.371 times 10 to the power of 6 to the power of negative 1/2. And that gives us 11,182 or 11,000, something like that. Makes sense. Say 11,000, just to round. This is going to be in meters per second because we have meters here, and then we're taking the square root. If you multiply it by meters in this quantity, in this thing here, the meters are going to end up canceling. Then you take a square root of that, meters squared. Square root of that is just meters. Square root of meters of seconds squared is just seconds. And of course, you can convert that into miles per hour if you so desire. If the distance is doubled, what happens to the escape speed? Well, here we're talking about if we double the distance, we're getting c times twice d to the negative 1/2. We can, of course, distribute that over 2 and d. And this can rearrange to 2 to the negative 1/2, c d negative 1/2. And this quantity here is the same thing as this. So this is the same thing as saying 2 to the negative 1/2 times the original velocity. 2 to the negative 1/2, of course, is just 1 over 2 to the 1/2, which is the square root of 2. In other words, if the distance doubles, then what we're doing is we are reducing the velocity by the square root of 2. And like I said before, if the distance doubles, then the velocity gets smaller. If one increases, the other decreases. This is just another way of showing that inverse relationship, as this is called. Okay, breaking distance d can be modeled by this equation here, d equals kv squared. K is just some constant. It really depends on the situation. Most typically is like if there's ice or if the road is wet. V is the speed. Again, if direction, then velocity. And then what's the relationship when solved for v? Well, the first thing I'm going to do here is divide by k. And we get v squared equals d over k. And then I can take the square root of that. Now, technically, when we take a square root, we have to concern ourselves with plus or minus, but not in this case. We're talking about physical quantities here. There's no real reason to talk about velocity negative since we're only talking about one direction, but that's why I'm ignoring that part of this. But what's interesting here is that I can actually break up the radical over the top and the bottom. And the square root of k, this is the same thing as saying 1 over the square root of k times the square root of d. 1 over the square root of k, well, k is already just some constant. So 1 over the square root of k is just, again, some other constant. Like it's some distant number. You can solve for it if you know what k is in the beginning. But I can just give this a different name. For instance, I could just say k2 times the square root of d. It's just some different, it's not k, right? It's definitely not k, unless k were 1, I suppose. But it's some constant that we know from k. As long as you make the statement that k squared equals 1 over the square root of k from what we originally know. But again, it's just some constant. Now, if distance is doubled, how does this change speed? Well, we have the velocity. Again, what we found out here was that v equals some constant times the square root of d. That's the same thing as d to the 1/2 power, again, by rules of radicals. Then if we're going to double the distance, that's what we have here. I can break up the radical. And this is the same thing as the square root of 2 times k2, the square root of d. And again, this is just the original velocity that we were talking about. So it's the square root of 2 times v. In other words, if we double the distance, then we multiply v, the original velocity, by square root of 2. Square root of 2 is approximately, this is approximately 1.4. It's a number larger than 1, which means if I double the distance, I increase the velocity by 1.4 or 40%, something like that. So if d increases, then v increases. Let's say if d increases, v increases. Whereas before, right up here, if d increased, then v decreased. So this is a showing of an inverse relationship for escape speed, and for braking distance, this is a direct relationship. One increases, the other increases, and vice versa. If one decreases, the other decreases. All right, the last thing I want to talk about here is standard deviation. It's very, very commonly used in statistics, and data sciences uses a lot of stats in it. And this is how you solve for the population of a standard deviation. The standard deviation of a population, I should say, is with this formula. It's a little cumbersome to talk about with this way, and normally we like to use computer software to do the calculations because it's very hard to do. It's very time consuming when you have a very, very, very large data set, which is pretty typical for data sciences. What this means, this is actually lowercase sigma here, and this is capital sigma. Capital sigma in mathematics means the sum of. And so the way of writing this is the same thing as saying we're summing up over all of the numbers in a data or data points in a data set. It's the same thing as saying x1 minus, this is the mean mu squared, plus x2 minus the mean squared, x3 minus the mean squared, and all the way on up to xn, because there are n points. That's what the lower part, that means there's n data points in this set, minus the mean squared. That's the summation. And we have all this divided by n and the square root of this entire thing. Now, what can we use here? What rules of radicals? Well, we can break up the radical on top and bottom, but the radical cannot be further broken up over addition, right? The rules of radicals does not have anything. I can break it up over multiplication, but not addition. So the best we can do here is just take the square root of this sum. I'm not going to write the actual breaking up over it. It's just too time consuming. But I can write this over the square root of n. Now, if we have a set 1, 3, and 5, what's the standard deviation of the set? Well, the first thing we have to do is find the mean. The mean mu is going to be 1 plus 3 plus 5 divided by the number of numbers there, which is 3. That's the same thing as 9 over 3, or 3. Now, we can do x1, which is going to be 1 minus the mean squared, plus x2, which is going to be 3 minus the mean squared, x3, which is this is 5 minus the mean squared. The square root of that over the square root of the number of numbers, which are 3 in this set that we've designated here. Okay, we want an exact answer with rationalized denominator and a numerical approximation. That's what it's saying here in this last part. So 1 minus 3 is -2. -2 squared is 4. Then 3 minus 3 is 0. 0 squared is just 0. And 5 minus 3 is 2. 2 squared is 4 over the square root of 3. Get the square root of 8 over the square root of 3. The square root of 8 can be rewritten as 4 times 2. I can break up that radical over the 4 and the 2, giving me 2 root 2. And finally, I can rationalize the denominator by multiplying top and bottom by root 3. That gives me 2 root 6 over 3. This is an exact number. We can find the numerical approximation by plugging it into a calculator. So we get 2 times the square root of 6 divided by 3, and we get 1.63. So this is approximately 1.63.